Let's do an example here. Let's imagine that we've got an organic molecule. So I'm going to use an organic molecule, chloromethane. So chloromethane, or it's also known as methyl chloride, is basically a carbon. So we have a carbon and we got the three little hydrogens hanging off one end of it and a chlorine there. Okay. And so this is going to be a polar molecule. This end's going to be negative, that end's going to be positive. And so it turns out that the chloromethane molecule has a dipole moment of 1.87. They actually give it in debis. Okay, so if you convert that, turns out that a debi, which is used in molecular sort of dipole moments, debi turns out to be equal to debi is equal to 3.336 times 10 to the minus 12 coulomb meters. Okay. So that means that if we put this into SI units, that would be 6.24 times 10 to the minus 27 coulomb meters. Okay, so I want to know if we had an electron sitting out here and the electron was a distance of 142 nanometers from this molecule, I want to know what's the acceleration on the electron. Okay. All right. So just a free electron sitting out there. What's the acceleration on the electron? And so what we would do is we would say, well, we know that acceleration is F over m. Okay, that goes all the way back to physics 1. Okay, so what is F? F is going to be Q times E. Well, the electron has a fundamental charge, times E. Okay, the E, because the way I drew it, it was along the line of this. That means it's going to be like in the book, the electric field is going to be 2 K sub B P over Z cubed. So that would be 2 times 8.99 times 10 to the 9 Newton meter squared per coulomb squared times the P, the dipole moment, 6.24 times 10 to the minus 27 or 22nd coulomb meters, divided by, I said it was 142 nanometers, so that's 442 times 10 to the minus 9 meters, and that's cubed. So the electric field turns out to be equal to 3.92 times 10 to the 9 newtons per coulomb. Okay, so acceleration is F over m, so that's E over m. So that's going to be equal to 1.602 times 10 to the minus 19 coulombs times what we just calculated, 3.92 times 10 to the 9 coulombs per meter, divided by 9.11 times 10 to the minus 31 kilograms. So the acceleration is 6.89 times 10 to the 20 meter per second squared, which is a huge acceleration. So that basically means that because this thing is so polar, that the dipole fields are going to clear the area essentially of any free electrons in the area. There's not going to be any free electrons because if they're near the negative end of it, they'll go shooting away really, really fast. If they're near the positive end, they get pulled towards it really, really fast. And so that makes this a actually fairly reactive molecule. And so that's how you would apply this idea of electric dipoles, for example, to chemistry.